what I've got here is I've got a 161 counter here, and I have a 4040 counter here. Here's my clock. I've inverted the clock so that to the 4040, so they both look like they're counting on the rising edge of, or maybe I have it the other way around. No, it looks like we're looking at the clock before I invert it. So it looks like the 161's clocking on the falling edge of the clock, but it's not. I've got both I took the clock and I inverted it so that both of these would appear to count at the same point. And I'm looking at the lower 4 bits. Here's QA through QD and Q0 through Q2 of the 4040. Up here I have the count. This is the count for the 4040. This is count for the 161. They look sort of the same, right? What's the big deal? Why not just use this one if you need lots and lots of outputs and you don't need all the fancy loads and stuff? Well, let's zoom in on this. I'll stop it because it's a lot easier to see. OK, so here's our clock. This is the falling edge of the clock. And this is the point where we go from a count of 1, 1, 1, 1 to 0, 0, 0, 0. And you notice for the synchronous counter, all of the output bits change at essentially the same time. This is 20 nanoseconds per division. OK, notice there's a delay between when the clock happens and actually the rising edge of the clock's over here. Then we invert it to get the falling edge of the clock. So the rising edge of the clock is over here. So there's a delay of around 40 nanoseconds or so. But then everything changes at the same time. Whereas notice what happens with the 4040 is the least significant bit goes from 1 to 0. That causes the next bit to go from 1 to 0. That causes the next bit to go from 1 to 0. That causes the next bit to go to 1 for 0. And sooner or later, it causes the 12th bit to go from 1 to 0. And notice the 12 bits changing way over here. Our clock's over here, 20, 40, 60, 80, 100, maybe 100 to 120 nanoseconds later. Now, if we don't care about the delay, that's fine. But notice that if we're using this counter and we need all 12 bits, we don't know that we have a valid count until on the order of 100 to 120 nanoseconds. That limits how fast we can run our system. We have to wait that long after a clock to make sure that the count's valid. Whereas here, it looks like we have to wait somewhere between 20 and 40 nanoseconds. So there's a significant difference. Simone?
If you're waiting, wouldn't it still be counting now?
Depends on how fast the clock is, doesn't it? I obviously can't clock this faster than it takes for this thing to settle. So my clock has to be, if we're talking 100 nanoseconds, well, a nanosecond is a megahertz. 100 nanoseconds, 100 kilohertz. So I have to wait. Did I get that right? It's always dangerous when I do exponents in my head. No, 10 megahertz. Sorry. Yeah. But we have to wait on the order of, say, 8 times longer, which means we have to run the system 8 times slower. Whereas this one, we know that 20 to 40 nanoseconds after the clock, we could give it another clock if we wanted. So, on the other hand, if all we care about is this output, and we don't care there's a delay, we don't really care that these others take longer. So it's nice to have a counter that we can use to get a lot of bits and a big divisor ratio without having to put 3 or 4 16-bit packages together. So, they each have their purposes. We use the right one in the right circumstances.